All right, welcome to another deep dive, everybody. Today we're going to be exploring how we can make AI that actually, knows things,
Uh-huh.
like really knows things,
Yeah.
and then uses that knowledge to actually, like, make smart decisions.
Right, right.
So this whole deep dive is really inspired by, some really interesting stuff that you shared with us that's really got us thinking about what it actually means for an AI to be more than just a very, very, fancy calculator.
Yeah. I mean, I think a lot of people are thinking about this these days, right?
Yeah,
It's kind of like, how can we go beyond these AIs that are just really good at one specific thing?
right.
Like, some AIs are really good at playing games or, navigating from one point to another on a map.
Yeah.
But how can they start to kind of understand the world in a more general way?
Right, and how can they sort of use that more general knowledge for all sorts of different things, not just one specific thing? And I think this is something that, when we were looking back at some of the stuff from those earlier chapters, like chapters 3 and 4,
Yeah.
those agents, while they were brilliant at what they were designed to do,
Yeah.
they had a very, very narrow view of the world, right?
Yeah. Very limited knowledge.
It's like they couldn't even grasp, like, the most basic, common sense things that we just take for granted.
Like what? Give me an example.
Like, you can't have a road that has a negative length.
Uh-huh.
That's just nonsense.
Right.
Or like, two things can't occupy the same space at the same time.
Yeah.
Those are like basic rules of the world, but those agents in chapters 3 and 4, they don't even know that.
Right. They only know what you tell them.
Exactly. And their knowledge was just so specific to
Mhm.
that particular task.
Yeah, very task specific.
And this becomes especially tricky when you have, an agent that can't directly observe everything in the environment.
Oh, yeah. Like those partially observable environments we were talking about.
Exactly.
Yeah.
Partially observable environments. And, for those simpler agents, trying to represent their understanding of the current situation often involve, like, just listing every single possible concrete state that the world could be in. Right. And can you imagine trying to do that for something like, uh, drive to a U.S. town with a population under 10,000?
Oh my gosh.
You'd have to literally list out all the thousands of towns that fit that description.
It'd be impossible, right?
It'd be incredibly inefficient,
And just totally inflexible.
totally inflexible.
Yeah.
And thankfully, um, we did start to move in a better direction with that idea of factored representation that we talked about in chapter 5.
Right.
Right. Instead of exhaustively listing every single possibility, we started representing situations by assigning values to key characteristics.
Yeah.
But, today we're going to take an even bigger leap. We're going to talk about using logic as a really powerful way for AI, and these are these knowledge-based agents, to actually represent, what they know about the world.
Right. So, like, instead of just giving the agent, like, a list of specific instructions for every single possible situation,
Right.
we can give them a set of rules, like, more general principles, almost like a scientist.
Right.
They use their knowledge of, like, physics or chemistry to solve a whole bunch of different problems.
Uh-huh.
So these knowledge-based agents, they can take information from different places, combine it intelligently, and apply it to tons of different situations.
Yeah, and that's what makes them so powerful, right?
Yeah.
They're not just limited to one specific task.
And they can adapt too, right?
Right.
Like if their environment changes or if they need to learn something new, we can tell them new facts about the world and they can update their knowledge so they can become competent a lot faster.
Okay, so let's dig into this a bit. What exactly is what defines a knowledge-based agent? What are the key components?
All right, so the heart of a knowledge-based agent is its knowledge base,
Okay.
or, we call it a KB for short.
KB.
And it's basically a set of sentences, but not just any sentences. These sentences are expressed in a special language. We call it a knowledge representation language.
Okay.
And each sentence makes a statement about the world, like a fact or a rule. Sometimes these initial statements are called axioms,
Axioms.
which are things we just assume to be true.
Okay, so you have this KB, and it's full of these sentences, these axioms, that describe the world.
Yeah.
But how does the agent actually use that knowledge?
So there are two main operations that the agent can perform on its knowledge base.
Okay.
We call them tell and ask.
Tell and ask?
Yeah. We use tell to add new information to the KB, essentially telling it a new sentence.
Okay.
And we use ask to query the knowledge base, like, asking what it knows.
Okay, that makes sense.
And both of these operations can sometimes involve inference,
Inference.
which
Oh.
is like the process of deriving new sentences from existing ones.
So the AI can essentially, like, figure things out on its own based on what it already knows.
Exactly. It's using logic to deduce new information.
Wow.
But, it's really important that these new sentences actually follow logically from what's already in the knowledge base.
Right, so it's not just making things up,
Exactly.
actually deducing things
Yeah.
based on logic.
Yeah.
Okay, that's really cool. So how do these components like the KB, TL, and LSK,
Mm.
how do they all kind of work together in an actual agent?
So you can think of it like this. The agent gets some input from its sensors, right?
Uh-huh.
Like in the Wumpus world, it might sense a breeze or a stench,
Okay.
and it translates that perception into a sentence and tells it to its knowledge base.
Okay.
Then, when it needs to decide what to do, it asks as the KB for the best action to take based on everything it knows. The KB does some reasoning and gives back an action,
Okay.
and then the agent tells the KB which action it took, so it can update its knowledge about the world.
That sounds like those simple tell-all and ASK operations are actually doing quite a lot of work behind the scenes.
Oh, yeah. There's a lot of complex processing going on there.
So how do we actually, like, analyze the behavior of these agents? It seems pretty complicated.
Well, the cool thing is that we can analyze them at what we call the knowledge level.
Okay.
We can focus on what the agent knows, like its goals and its understanding of the world.
Uh-huh.
And from that, we can understand why it's behaving the way it is without having to worry too much about the specific details of how it's implemented.
Okay.
Like what data structures it's using to store the knowledge or the exact algorithms it's using for reasoning.
So we don't need to know all the nitty-gritty details of the code to figure out why the agent is doing what it's doing.
Exactly. Think about that taxi example from the book,
Okay, yeah.
If the taxi knows it needs to get from San Francisco to Marin County, and it knows that the Golden Gate Bridge is the only way to get there, then we understand why it's going to choose to take the bridge.
Right.
We don't need to know whether it's using, like, a complex digital map or just some abstract understanding of the city's layout.
That makes sense. So basically we can just tell the agent what it needs to know about the world, and it'll be able to figure out how to act.
Yeah, that's the idea behind the declarative approach. We're just giving the agent the knowledge it needs.
Declarative approach, okay.
The other way is the procedural approach, where you actually write code to tell the agent exactly what to do in every situation.
Okay.
There was a big debate for a while about which approach was better, but now most people think that the best AI systems actually use a combination of both.
Okay.
They use declarative knowledge for things that need to be flexible and adaptable, and procedural code for things that need to be really efficient.
So it's not one or the other, it's a mix of both.
Right.
And I remember reading in chapter 19 that some researchers are even working on agents that can actually learn and build this general knowledge on their own, right?
Oh, yeah, that's a whole other fascinating area.
Yeah, that's pretty wild.
Yeah.
So this all makes sense in theory, but I'm curious to see how this approach actually works in a more challenging real-world scenario.
Right. Well, that's where the Wumpus world comes in.
The Wumpus world, okay.
It's a classic example in AI, kind of like a thought experiment.
Okay.
So imagine you have an agent exploring a cave.
Okay.
And this cave, it's made up of a bunch of interconnected rooms.
Okay.
And somewhere in this cave, there's a Wumpus.
A Wumpus. What's a Wumpus?
Well, a Wumpus is a dangerous creature. And if the agent runs into it, well, let's just say things don't end well for the agent.
Okay, so it's like a monster.
You could think of it that way, yeah.
Okay.
And to make things even more challenging, there are also pits scattered throughout the cave.
Pits, like bottomless pits.
Yeah, exactly. If the agent falls into one, that's it. Game over.
Oh, man. This sounds dangerous.
It is. And to top it all off, the agent only has a single arrow to defend itself with.
One arrow. So it only gets one shot.
That's right.
But there's a reward, right? Like, why is the agent even in this cave?
Ah, yes, the reward. There's a chance to find glittering gold hidden somewhere in the cave.
Okay, so it's like a really dangerous treasure hunt.
Exactly.
High risk, high reward.
That's the Wumpus world.
All right, so let's break this down a bit more. We always like to use that PEAS framework to describe these scenarios.
Right, right.
So for the Wumpus world, what's the performance measure? Like, how do we know if the agent is doing well?
So the goal is to get out of the cave with the gold, and that gives the agent a big positive score.
Okay.
Falling into a pit or running into the Wumpus, those are big penalties, like the worst possible outcome.
Right.
And even using up actions like moving or turning, those also have small penalties.
Okay, makes sense. So what about the environment? You said it's a cave with rooms, but can you be more specific?
Yeah, so typically the Wumpus world is a 4 by 4 grid of rooms,
Okay.
and the agent always starts in the bottom left corner,
Okay.
position of 1-1, facing east.
Facing east. Okay.
Now the gold, the Wumpus, and the pits, they're placed randomly in the other rooms,
Okay.
but the starting room is always safe.
Okay, so the agent doesn't have to worry about immediately falling into a pit or getting eaten by the wumpus right when it starts.
Exactly. This has a chance to explore and figure things out.
Okay, that's good. So what actions can the agent actually take in this cave?
Okay, so it can move forward to the next room.
Okay.
It can turn left or right 90 degrees.
Okay.
It can grab something if it's in the same room.
Like the gold, hopefully.
Right, hopefully.
And it could shoot its arrow.
Okay, but only once, right?
Only once. Yeah, okay. That's important.
And finally, it can try to climb out of the cave, but that only works if it's in the starting room.
Okay, so these are the actions. But what happens if the agent, tries to walk into a wall?
Well, it'll bump into the wall and stay in the same room.
Okay.
No harm done, but it wastes an action.
Right, and we already said that running into the wumpus or falling into a pit is, not good.
Yeah, that's the end of the game for our agent.
All right, so we've got the actions covered. What about the sensors? How does the agent actually perceive its environment?
So the agent has 5 different types of sensors.
5, okay.
It can smell a stench if it's in a room next to the Wumpus.
So not diagonally.
Right, just in the rooms directly north, south, east, or west of the Wumpus.
Okay, so the wumpus is pretty stinky.
Yeah, you could say that.
Okay, what else?
It can feel a breeze if it's in a room next to a pit.
Okay,
It'll see glitter if the gold is in the same room.
okay,
It'll feel a bump if it tries to walk into a wall.
right.
And it'll hear a scream if it successfully kills the Wumpus with its arrow.
Okay, so it's getting a lot of information about its surroundings, but it can't see the whole cave, right?
That's right.
It's only getting local information from its immediate surroundings.
Yeah, it doesn't have a map.
So how do we characterize this kind of environment in, AI terms?
Well, the Wumpus world is what we call a deterministic environment,
Deterministic, meaning
the outcome of any action is predictable.
what?
If the agent moves forward, we know exactly what will happen based on where the walls and the Wumpus and the pits are.
Got it.
It's also a discrete environment, meaning the world is made up of distinct separate rooms.
Okay.
It's not a continuous space like the real world.
Right.
It's static, meaning the Wumpus and the pits don't move around once the game starts.
Okay.
It's a single agent environment because we're only focusing on our one exploring agent.
Right.
It's sequential, meaning the order in which the agent takes actions matters a lot.
Okay.
And as you pointed out, it's partially observable.
Right, because the agent can't see everything.
Exactly.
So it seems like that initial lack of knowledge about the cave's layout is the biggest challenge here, right?
Oh, absolutely.
I mean, how can the agent possibly know where to go safely if it doesn't know where the dangers are?
That's the whole point. The agent starts off not knowing anything about the cave except for the fact that its starting position is safe.
So how does it figure things out?
Well, that's where the logical reasoning comes in.
Okay.
The agent has to use its knowledge of the rules of the Wumpus world and the information it gets from its sensors to make inferences about what's in the other rooms.
Okay, so it's like a detective using clues to solve a mystery.
Exactly.
And can it always find the gold and get out safely? Or there's some caves where it's just impossible.
Well, in most cases, there is a way to find the gold and escape,
Okay.
but it requires careful reasoning and sometimes a bit of calculated risk-taking.
Uh-huh.
But yeah, there are some cave configurations that are just too dangerous.
Boy.
Like the gold might be surrounded by pits on all sides.
So there's no way to get to it without falling in.
Right, or the Wumpus might be blocking the only exit.
That's rough.
Yeah, it can be a cruel world, even in a thought experiment.
So how does a knowledge-based agent actually go about exploring this cave? Can you walk us through like a specific example?
Sure, let's imagine our agent is starting in room 11 as usual.
Okay.
It knows that this room is safe.
Right, that's part of its initial knowledge.
And its first perception is none, 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 none.
Okay. So no stench, no breeze, no glitter, no bump, no scream.
Exactly.
Yeah.
So what can we conclude from that?
Well, seems like it's safe to move to the next room.
Which room?
Either 12-2 or 2-1, right?
Right. The agent can infer that those rooms must also be safe because If there were a wumpus or a pit nearby, it would have detected it with its sensors.
Right, because the stench and breeze only travel one room away.
Exactly. So the absence of those percepts actually tells us something important.
That's really cool. So let's say the agent decides to move to 201.
Okay, and when it gets there, its perception is none, breeze, none, none, none.
Okay, so now it's feeling a breeze.
Uh-huh.
What does that tell us?
Well, we know that a breeze means there's a pit in one of the adjacent rooms.
Okay.
But we already know 11-1 is safe.
Right.
So the pit must be either in 2-2 or 3-1 or maybe both.
Okay, so it's narrowed down the possibilities, but still doesn't know for sure. What should it do next?
Well, at this point, the agent could go back to 11-1 and then explore 1-2, since that's the only other room it knows is safe.
Okay, so it backtracks a bit.
Yeah.
Let's say it does that and enters Quan 2.
Okay, and its perception there is stench. None. 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 None.
A stench. That means the wumpus is nearby.
Right, and because it didn't smell a stench in 11-1, and we've already established that 2-1-2 might have a pit, the wumpus must be in 153.
Wow, it's like it's piecing together the clues, Sherlock Holmes style.
Exactly. It's using its knowledge of the rules and its observations to deduce new information.
This is really neat.
And it gets even better. Because there's no breeze in 12-2, the agent can now also conclude that there's no pit in 2-12.
Oh, right, because if there were, it would have felt a breeze.
Exactly. So now it knows for sure that the pit must be in 3-1.
So it's actually using both the presence and the absence of percepts to refine its knowledge.
Exactly.
That's pretty sophisticated.
It is, and this is how the agent can gradually build up a more complete understanding of the cave.
Okay, so let's say the agent continues exploring and eventually finds the gold. What happens then?
Well, let's say it stumbles upon the gold in room 2-3, and its perception is stench, breeze, glitter, none. None.
Okay, so it's found the gold, but it's also next to both a wumpus and a pit.
Yeah, that's a pretty precarious situation.
What should it do?
Well, the best course of action would be to grab the gold and then try to get back to the starting room as quickly as possible.
Climb out of the cave.
Exactly.
So the whole point of this wumpus world example is to show how an agent can use logical reasoning to navigate a complex environment, right?
Right. It demonstrates how the agent can combine its initial knowledge with the information it gathers from its sensors to make safe and effective decisions.
And you said earlier that all the conclusions the agent makes through this reasoning process are guaranteed to be correct.
Right. Well, they're guaranteed to be correct if its initial knowledge and its sensory information are accurate.
Okay, so it all depends on the quality of the information it's working with.
Exactly. Logic itself is all about sound reasoning, but if the premises are wrong, the conclusions can be wrong too.
That makes sense. Okay, so we've been talking about logic a lot, but what exactly is logic in this context?
So logic is a formal system for representing knowledge and reasoning about it.
Okay.
It's a way to make sure that our reasoning is clear, precise, and unambiguous.
Okay.
Think of it like math.
Right.
An expression like 3 + 4 = 7, that's a well-formed statement in math.
Mm-hmm.
It follows the rules of arithmetic.
Right.
But something like +3, 4, that's just meaningless.
Yeah, it doesn't make any sense.
That's the idea of syntax in logic.
Syntax. Actually.
It's the rules for constructing valid sentences.
Okay, so it's like grammar for logic.
Exactly.
So logic has syntax, which is how we write the sentences. What else is there?
Well, logic also has semantics, which is all about the meaning of those sentences.
Okay, so syntax is the form and semantics is the meaning.
Right.
Okay, I'm following.
And in logic, the meaning of a sentence is determined by its truth value.
Truth value, meaning whether it's true or false.
Exactly.
Okay.
And the truth value of a sentence depends on the particular situation or world we're considering.
Like in the wumpus world, whether there's actually a pit in a certain room or not.
Exactly.
Okay, so these different worlds you're talking about, are they like different possible configurations of the wumpus world?
Yeah, you could think of it that way.
Okay.
But we usually use a more formal term for them, models.
Yes, okay.
So a model is like a specific, detailed description of a possible world. It tells us exactly which sentences are true and which ones are false in that particular world.
Okay, so it's like a complete picture of one possible way the wumpus world could be set up.
Exactly. And if a sentence is true in a particular model, we say that the model satisfies that sentence.
Okay, that makes sense. So we have these models that describe different possible worlds, and we have sentences that can be true or false in those models.
Yeah.
What about reasoning? How does that fit into this picture?
Well, reasoning is all about figuring out what logically follows from our knowledge.
Okay.
We want to be able to derive new sentences that are guaranteed to be true based on what we already know.
Okay.
And this process of deriving new true sentences is called logical entailment.
Logical entailment. Okay.
Yeah, and we say that a sentence, let's call it ush, logically entails another sentence. Let's call it ush.
Okay.
If ush is true in every model where ush is true.
Okay, so it's like, if I's is true, then absolutely must be true as well.
Exactly.
In all possible situations that are consistent with Osh being true.
Right, and we write this relationship as ICC AFA PET.
Okay, so it's like ISM clay easy, but in a very strong logical sense.
Right.
Can we go back to the Wumpus world for a sec to see how this entailment thing works in practice?
Sure. Remember that situation where the agent started in 11.1, no stunch, no breeze?
Uh-huh.
Then it moved to 2.1 and felt a breeze.
Yeah, I remember.
Okay, so all that information, plus the general rules of the Wumpus world, like how breezes and pits are connected, that forms our knowledge base, or KB.
Okay.
Now, we wanted to know if there was a pit in 12.2.
Right.
Let's call that sense, Abel.
Okay.
And we also wanted to know if there was pit in 2.2. Let's call that ESO.
Okay.
So to figure this out using entailment, we need to consider all the possible models, all the different ways that pits could be arranged in the relevant rooms.
Okay, like, is there a pit in 12.2? Is there a pit in 2.2? Is there a pit in 3.1?
Exactly. And we need to find all the models where our KB is true.
The models that are consistent with what we know.
Right. And it turns out there are only 3 such models in this case.
3 out of all the possible combinations.
Yeah, just 3. And if we look at those 3 models, we'll see that IA1, the sentence saying there's no pit in 12.2, is true in all of them.
Okay.
So we can say that KB Ugal is 1.
Our knowledge entails that there's no pit in 12.2.
Right.
But what about IA2, the sentence saying there is a pit in 2.2?
Well, if we look at those same 3 models, we'll see that IA2 is true in some of them and false in others.
Okay.
So we cannot say that KB equals 2.
Our knowledge doesn't tell us for sure whether there's a pit in 2.2 or not.
Exactly.
Okay, so that's how we use entailment to figure things out.
Right.
But how do we actually find all those models where the KB is true?
Well, that's where model checking comes in.
Model checking, okay.
It's an algorithm that basically goes through all the possible models and checks which ones satisfy all the sentences in our KB.
Okay, so it's like a brute force method of finding the right models.
Yeah, you could say that. And it's a very important algorithm because it's guaranteed to be sound.
Sound.
Meaning it only derives conclusions that actually follow logically from the KB.
So it's not going to tell us something's true if it's not actually true.
Right. It's very reliable in that sense.
But it also seems like it could be really computationally expensive.
Oh, yeah, it can be. Especially if you have a lot of sentences in your KB.
Because you have to check all the possible combinations of truth values for all the sentences.
Exactly. It gets really complex really fast.
So are there any other limitations to this model checking approach?
Well, another important property of inference algorithms is completeness.
Completeness, okay.
And that means that the algorithm can derive any sentence that is logically entailed by the KB.
So it doesn't miss any valid conclusions.
Right. And completeness can be a problem when you're dealing with logics that have infinitely many possible consequences.
Infinitely many.
Yeah, there are some logics where you can keep deriving new sentences forever. But for propositional logic, model checking is both sound and complete.
Okay, that's good to know.
Yeah.
But we've been talking a lot about sentences and models, all very abstract stuff. How does this actually connect back to the real world that the agent is trying to understand?
That's a great question.
Yeah, it's like we have all this fancy logical machinery, but how does the agent actually know if its knowledge base is actually reflecting reality?
Right. That connection is what we call grounding.
Okay.
It's all about how the symbols and sentences in the KB relate to the actual objects and events in the environment.
Okay.
And for our agents, the main way they ground their knowledge is through their sensors.
Okay.
So when the agent senses a breeze, for example, that sensory input is used to create a sentence in the KB that represents that perception.